Hi, good day. We are from Faculty of Mechanical Engineering, FKM in short, and our team consists of 3 members. So, me, Faiz Sulaiman, and Menotin, and also Adrian. So today, in our first project, we will be presenting about data and measurements for instrumentation and measurement subject. So, to start with, we will go with the introduction part of why we need instrumentation, why we need to measure. Okay, in our case, for Faculty of Mechanical Engineering, we need a fastener, basically screws and also bolt. Why we need that? Because for our case, when we do the study, they provide secure and high strength joints that can hold mechanical assemblies together under varying stresses and vibrations. Basically, for mechanical related problems, we usually deal with machines. Machines usually vibrate at high speed, as well as it produces a lot of force. So we need the fastener. So that is why we need to measure it properly. And second, we move on to the safety and reliability. So if let's say we make a machine, but without the fastener or bolts to hold it together, the machine will collapse within seconds due to the violent vibration and also the force. So in order to prevent the catastrophic mechanical failures, we must ensure that the bolt that we use, that we measure, must be totally the one that we have already designed, the one that has been designed by the machine maker. So that is the second part. And moving on, we go to the quantifying uncertainty. So what that means, basically, whenever we buy screws, also nut bolts or nuts, it does not usually perfectly the size that they have already stated. For example, if I say I buy an M10 bolt, it is not usually M10. Sometimes it can be M10.5, it can be 10.5 millimeter in diameter, or it can be less than that. For example, 9.5 millimeter. So that is why we want to quantify the uncertainty. We want to find the error and the error margin. Basically, whenever we scan a batch of fastener that we buy. Okay, now let's go to the objective and also the scope for our faculty. So, what's the primary objective for the project that we are doing right now, for the project that we are assessing right now, is to evaluate the dimensional accuracy of 15 machine screws and assess the reliability, precision, and practical limitations of using digital vernier caliper for critical length measurements. So, in short, we buy 15 screws. So from there, the 15 screws, we use it, we measure every single one of it, and to find the error margin, basically to find the tolerance, what's the range between what's the range for the screws that we bought, because it is not usually 15. It is not usually in the same size, because it can, due to the imperfections during manufacturing, it can vary a bit. So that is what we want to do. And also we want to test what's the limit for using digital vernier caliper. So moving on, we are going to further analyze, to further explain about the scope analysis. So we are not going to stray away from the scope that we've already stated, because ours is mostly on mechanical part. So for us, we are going to focus more on instrument performance, basically analyzing the reliability, ease of use, as well as precision of the digital measurement system. And after that, we go for the second part, in which it is the error identification. Basically, we just to investigate the potential systemic and also random errors that can occur within the digital vernier caliper. And lastly, we'll be focusing on the methodological constraint. Basically, we want to find what's the limitation of the digital caliper to detect minor changes in the screws, in the 15 screws that we are going to measure. So it is actually based on the design, and also based on the design of the screws, as well as the geometrical factor. So that's all for objective. Moving on to the background study for our project. So we can see that in the slide right now, we have the diagram of the fastener that we have already bought. Basically, all of the 15 fastener will be looking like that as shown in the slide. So we're starting first the measured dimension, basically the measurement. So the target parameter, our primary focus on this study is to study the overall length of the flathead screw of all of the 15 flathead screw. And for reference, we, unlike standard screws, usually measure from under the head. The length of the screws of the flathead screws that we already bought will be measured from the top of the flathead until the end of the tip, down to the bottom of the tip. And after that, we go to the second part, in which the mechanical importance of the dimension. So for the second part, we want to check the proper thread engagement. Basically, you want to make sure that it has the correct length. The correct length is ensured to be enough when the threads engage in mating material. Basically, whenever we screw it into certain material, the thread will be enough so that it won't sometimes over exceed, or it won't, usually over exceed won't be a problem because over exceed or under over or under it, less or more can be an issue. So we want to make sure to find the balance between it. And after that, for the second part, for the mechanical importance, we want to see what's the clearance and also the interference. Basically, we want to prevent the screw from bottoming out in a blind hole or protruding out the other side and interfering moving parts. So okay, for example, when we use the screw to measure the object, we want to make sure that whenever we screw it, it doesn't bottom. Basically, if let's say that thing is bottoming out, then there's no way that we are able to going to pull it out. And that is the first one. And the second one that will be our concern is about the protruding out. If let's say we screwed and the hole is not enough, the thread is not enough, and there's some sort of clearance interference between the thread of the screw and the object, then the material that we made, it will cause the screw to protrude out. So this will be a big concern, because if let's say the screw is to be protruded out, it will likely have a high chance to clash with the moving part of our machine. And lastly, we take a look at the metrology terminology and context. So measurement is basically the specific physical quantity being measured, in this case length, basically the top of the flat surface, from the flat surface up to the tip of the screw. And after that, we will be looking at the nominal value versus the actual value. The study, and for this case, we want to compare the nominal value, basically the intended design, the one that has been intended by the manufacturer, against the actual value, basically the one that has been manufactured. Basically, we want to see what's the difference in value between the one that is in design on CAD and the one that has been manufactured. So moving on. Okay, now we go to the instrumentation and also the measurement principle. So basically, for our case, we are basing on ISO 12385-1. So the application of the instrument in the project right now, as you can see, it has the internal jaw, the external jaw, and also the on-off, zero, and etc. So the primary measurement for this project, we only measure the external jaw to measure the overall length of the screw. And for future capability, we will use the caliper. Is also equipped with internal jaws and depth measuring rod, which follow the same general. Basically, when we for the caliper, it is shown here for future capability, is that the internal jaw, it can be used to measure to measure the the inner tube. Usually we use it to measure the inner tube because of the internal jaw. And the key feature, basically we have the lock screw. Pardon, we're going to move on to the key feature for this tool. We have the key feature. Basically the key feature, the lock screw, is actually the one that helps us to maintain the reading so that it won't stray whenever we take a reading and want to make sure what's the true. When we take a reading of a certain object and want to see what's the difference. So let's say we want to see the difference when we hold the instrument. We use the lock screw to make sure that it doesn't stray, it doesn't move around. So yeah, and also we have the 0 button. So for quick calibration, basically the third button. Basically, if let's say when we close, in usual case, for digital it's an easier one, because whenever we close a vernier caliper, when we notice that it's actually not aligned. I mean the line between the measuring line does not align. So we use a tare to make sure that it goes back to 0. And after that, we have the computer button to switch between two units, basically to switch between metric and imperial unit. So for our tool, the tool that we're using under any vernier caliper, the technical specification, we have the measuring range from 0 to 150 meter or 0 to 6 inches. The resolution, basically the smallest reading that it can capture, is 0.01 millimeter or 0.0 to the power of 3, 0.00045 inches for imperial unit. And the repeatability, basically the consistency of reading when measuring the same part multiple times, is also the same. So whenever we do the same reading, it will show the same reading. Basically, this is how repeatable. In other words, vernier caliper has a high repeatability, and the accuracy is plus minus 0.2 millimeter. Basically, the amount of deviation that will be expected when you measure this device is around 0.2 millimeter. And the measuring system used for this instrument is linear capacitive measuring system, and the maximum measuring speed is around 1.5 meter per second. It's not that fast, and usually the working temperature is around 5 to 40 degrees Celsius. Basically, the instrument will not work. Basically, the digital reading will not work if it is sub-zero temperature or it is around boiling water temperature. That's all for the instrument, for the measurement principle for vernier caliper.
Okay, now let's take a look at the methods to reproduce on how exactly we can measure the overall length of the screw. As we know, we are going to be using a digital vernier caliper, as I have in my hand right now, and we are going to be following the process of SPC project to measure machine screws that we have, which has a nominal length of 12 mm. In this case, we are just going to be using the outer diameter of the vernier caliper, which is this side, to measure the overall length of the screw. Although vernier caliper itself has a lot of multiple usage, but our focus is going to be on one part, and we're going to focus on how exactly to reproduce the method. So first of all, we need to prepare some samples of screws. We have a total of 15 machine screws, and we are going to divide them into 5 subscrews. With each subscrew, we'll be having up to 3 machine screws in random. And then we are going to be cleaning any debris or any stuff from the machine screw, as well as the edge of the vernier caliper itself, to prevent any kind of debris being stuck, which can cause an error reading. Next, we are going to be using the zero feature with the digital vernier caliper for zero to prevent the zero error reading. So what we have to do is basically, I'm just going to show you, and the slide itself has already shown what exactly it looks like. We're going to fully close the vernier caliper's jawline, as you can see right here. Right now it's having a reading of 0.00, and if it says something like negative of any values, we're just going to press the 0 button over here, and it's just going to reset to 0. So now we have already completed our zero calibration, and we can proceed with the next step. Okay, now that we've done the zero calibration, let's do another method, which is called the traceability, where we can ensure the verification of the instrument itself. Although It is to be noted that in our case, we don't actually have a actual certified reference block to exactly know whether or not multi the caliper itself is reading the exact dimension. But we can do an uncertified method, which in our case we decided to use the 1 millimeter thickness of a printed TPU, and we are going to use the vernier caliper itself to measure the thickness. As shown in the picture, it is showing a reading of 1.03 mm, which is very close to 1 mm, and we know that the 0.03 mm is coming from the instrument error of plus minus 0.002 mm. So now that we have found a way to verify whether or not the instrument is actually measuring the value of distance correctly in millimeters, we can proceed with the next step, which is measuring the screw. So what we have to do is have a sample of screw as mentioned before in our hand, and we are going to simply retract the closed jaw of the caliper by simply sliding down this roller. Once you have slid down to fit the sample of the screw, you're going to ensure that the flat head of the screw is in parallel with the upper jaw, and the bottom part of the screw is also parallel. Make sure it is not slanted, make sure it is straight as possible to prevent any misreading from the screw itself. And as a method of precaution, we can actually use this top screw gauge and twist it to lock it, and we can actually have our proper reading. In our case, right now it's reading 11.49 mm of overall length. And later we're going to see the difference of length the screw is going to be having, but 11.49 is considered the right amount of length for this machine screw especially. And to show the repeatability, we are going to be measuring the same screw up to 3 times, and we're going to be averaging. In our sample, we have measured a screw which resulted in 11.51 mm, 11.52 mm, and 11.53 mm, giving an average of 11.52 mm of the screw length. So that's for just for a single screw, and we're going to repeat the process for the next 14 screws and so on. So now that we have already measured and recorded the 15 sample screw data along with their subsets, we can actually tabulate them in the data so that we can graph out our SPC control as well as to find the difference between the nominal length of the screw and the measured value. This is purely part of the project, and it shows that the instrument is helpful in achieving these kind of projects. So let's take a look at the example of what we have tabulated. So we can see on by using the digital caliper, we have screw 1, screw 2, and screw 3 in the top row, and we have subsets of 1, 2, 3, 4, and 5. And the recorded length, like 11.4, 11.44, 11.33, are the recorded length with the caliper, which is the average length of 3 readings per screw, and we have recorded in a table data. So the SPC is basically just going to rely on the average value of the overall length of the screw, the range of one subset by subtracting the maximum value with the minimum value, and also the average range for each subset. And with that, we are just going to be plotting the upper control limit, the lower control limit, the average reading, as well as the range as well. This is going to give us an idea of whether or not the machine screw is consistent with their process, and whether if they exceeded the lower control limit or upper control limit. So we are going to be looking at some graphs later on to understand how exactly the project is achieved. So now that we have already established our graph, we can take a look at the results and explanations from the project we have done. So first of all, let's take a look at the average length of screw versus the nominal length of screw. The machine screws are supposed to have nominal length of 12 mm as per the data sheet that's being attached along with the purchase screw. And we know that from a record, it is not exactly 12 mm, but they are in the average range of 11.3 up until 11.55 mm. So from this data, we can understand the 515 interval screws against the intended design target. And every single measure screw actually fails and completely below the rate nominal line of 12 mm. And this is purely because of the systematic error of machining, which indicates that the machine or setup is constantly producing screws that are too short compared to the design specifications. But now let's take a look whether or not if it's acceptable in terms of SPC. In SPC, it's we have established based on the screw readings purely, and we have established the upper control limit, which is the yellow line on the right graph, and the lower control limit, which is the green line on the right graph as well. And we can see the blue lines with the dotted are actually the actual readings of the screw from each subset, which is a total of 5 subsets, and we can know the average is around 11.5 mm in total. So with this, we know that SPC shows the average across 5 subgroups, grouping the 15 groups to check for the process stability. And all the subgroups averages along the blue line and fluctuates naturally but stay completely within the upper limit and also the lower limit, which is considered actually a good process and is actually safe to proceed. And what we can do to improve the machining aspect is that we can simply introduce the overall length to produce by a small scale so that it actually reaches the 12 mm line as intended. But in overall, none of the screws have exceeded the upper control limit or lower control limit.
So to ensure that our data is as accurate as possible, we begin with a verification check. So we check if this digital caliper um, is is giving or is providing us an accurate value and a reasonable reading. So what's the major advantage of using digital caliper is that it eliminates a human parallax error, which is I think is quite common errors to find in the measurement world. So basically, what is that a mistake is the person mistake of reading scale at the wrong angle. So while allowing for faster data collection, it also eliminates parallax error if we use this digital caliper. So by zeroing the instrument at a fully closed position before each measurement is taken, we effectively remove any baseline offset from our recorded values. So second thing that I want to talk about is that because in measurement world, consistency was the priority. We used a standardized measurement procedure throughout the study. So basically, we measured the flathead screws from the top of the head to the bottom tip using identical contact point every time we measured the screws. So this rigor reduces variation caused by inconsistent technique, because we know that in the world of measurement, consistency is quite important, and also the accurateness of data. So for repeatability, each screws was measured 3 times. So after that, we recorded the average value as the final length of our SPC analysis. So why do we do that? So this will help us to identify random variation and build higher confidence in our final results. So while our process was kind of rigorous, I would say, we must acknowledge each instrument have their own limitation. So first of all, I want to talk about is our resolution limits. So our readings are strictly limited by digital solution of 0.01 mm, because any variation smaller than this cannot be detected by the hardware. This is one of the major limitation of the digital caliper. The second thing is that the contact geometry itself, because of the caliper jaws measure point to point contact, they cannot assess the actual geometric profile or the curvature of the screw tip, which is a factor in our uncertainty estimation. So the third thing that I want to talk about is that potential errors that we might have in doing this experiment is that we remain vigilant regarding the systematic errors such as zero offset, which is caused by dust or maybe debris trapped in the jaws before we start zeroing it. So another thing that I want to talk about is that to further minimize external variables, all measurements were conducted by the same user in consistent room environment, which is quite important because if we take in a different room, the temperature of or the room environment might be different. So regarding the traceability, we acknowledge that while our verification process was kind of robust, full of metrological traceability, would require the use of certified reference standards. But However, our current approach remains highly reliable for the scope of this project. And in summary, and the conclusion that I want to make is that our measurement strategy is not just a set of steps, but an integrated system designed for reliability. This approach aligns with international standards. Specifically, the first one is ISO 10012, which control the measurement management system. Second one is ISO 133851 for the metrological characteristic of the calipers. The third one is ISO Guide 983. This is to evaluate the measurement uncertainty. So, by following all of these benchmarks, we ensure that our findings are technically sound and statistically significant. So, continuing on our final slides, which is our conclusion slides, we can summarize that our findings is quite significant, and we confirm that the digital caliper was an effective and reliable tool for capturing dimensional variations. This digital interface proved a very superior to traditional tools such as the digital caliper, such as the analog calipers, because it significantly reduced human errors such as, or specifically the parallax errors, while the quick zeroing function can make our work faster and more accurate, and we can minimize the errors as much as possible. So the second thing that I want to talk about is that the reliability of our method. We establish a high confidence in our reading. We are very confident in our readings because our techniques prioritizing reliability of our method or method reliability is because we standardize our measurement techniques. We ensure that every alignment is the same for every sample, and adhering to strict pre-use zero checks in line with one of the ISO standards. We were able to achieve, I think, we can achieve excellent repeatability throughout the study because 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 of we following the standards or the guidelines of the measurement techniques. So the third thing I want to talk about is we also identified some constraints, because I think we think that one of the important things is that each measurement or each experiment we have to acknowledge the constraints of this process. While our methods were accurate enough, the ultimate accuracy was limited by the nature or the manual nature of the measurement itself, specifically the variable force applied during handling or some external thing that we can control. But furthermore, while our internal verification was successful, um, the absence of a certified standards means full metrological traceability remains an area for future improvement because I think an experiment without a proper certified reference standard quite is still not that accurate. So, in order to be as accurate as possible, we need to have the reference of standards so that our experiments is data or readings as is very accurate, and the data um is consistent. So I think that's all from us, and thank you.